I'm Mark Kavanaugh for Kevy Coaches, and today I'm going to coach you up on fluid dynamics, fluids in motion. In this video, we're going to talk about fluid dynamics, which is just fluids in motion. So let's review what an ideal fluid is with a couple more properties. So going back to the previous video, we know that an ideal fluid has now four specific properties. One that's incompressible, which means that no matter the force applied, the fluid's volume is not going to change. So there's no change in density, so we can't compress that fluid to make it more dense. There's no resistance to flow, so that's non-viscous. So the viscosity is based on the stickiness or the thickness of the substance. So low viscous fluids would be water and rubbing alcohol. High viscous fluids would be honey syrup and molasses. Now we're going to add a couple of properties. The other two is that the fluid is steady. The velocity, density, and pressure are going to remain the same at each individual point, so nothing's going to change. And there's also no turbulence. So what turbulence is, you probably recognize this from an airplane, is all motion is translational. There's no rotational motion, or called eddy currents within the fluid. So that would be fluids flowing in different directions than the direction of most of the fluid, which is what causes that turbulence. So an example is if we place a wheel in the fluid, it would only move translation, it would not start to rotate. So let's go through some vocabulary. So let's define flow rate first. So flow rate is defined as the amount of volume passing through a cross-sectional area over a period of time. With an ideal fluid, if the flow rate is going to be constant. And the flow rate can be calculated by using the volume divided by the time. And the SI unit for flow rate is meters cubed per second, so volume per time. So that's the rate at which water is passing through or fluids passing through a given volume. As we see here, we have a pipe that has two cross-sectional volumes. So we'll call them 1 and 2. And those cross-sectional volumes are going to be equal. So the volume at 1 is equal to the volume at 2. And those volumes they're not a separate part of the pipe. We're just looking at a piece of the pipe. Now, in continuity with flow, conservation of mass is what is the result in the continuity of the fluid flow. So that means that the fluid is going to be flowing the same through 1 and 2. So that means the mass that goes through 1 is going to be the same as the mass that goes through 2 in that same period of time. Now the volume per unit time, or the flow rate of water flowing in the pipe, is constant throughout the pipe as well. So that's what dictates the conservation of mass. Let's mark some specific sections on the pipe. So we're going to mark the length of the volume we're looking at 1 is delta x1, and we'll mark the length of the cross-sectional volume of 2 as delta x2, and we'll also mark the areas as A1 and A2 for each of those volumes as well. Now, the same mass of water passes through section 1 and section 2 each second. So the flow rate's constant. The same amount of volume passes through, which means the mass is constant. So using conservation of mass, M1 is equal to M2. Now, we also know that mass is equal to density times volume. So we can substitute in the density of the fluid times each of those volumes that we're looking at, V1 and V2. But we also know that the volume we can find of a cylinder is the cross-sectional area times the length, which is A1 times delta x1 and A2 times delta x2 to substitute in the volumes. Now, we can go back to our kinematics since the speed of the water is constant. Using kinematics, we know that delta x is going to equal v times delta t. So we can substitute in the speed times delta t in for x1 and delta x2, and we get this big long equation. But what we know is that the density of the fluid doesn't change, so the density can cancel out. And because the water is passing through the pipe, and we know that the flow rate is constant, so the same amount of mass is passing through 1 is through 2, that means the time that it takes for the water to go delta x1 and delta x2 is going to be the same as well. So we can cancel out delta t1 and delta t2. And that leaves us with the equation of a1 v1 equals A2 times B2. And this is known as the continuity equation. So let's look into the continuity equation a little bit more. So A1 V1 equals A2 V2. So A1 and A2 are just the cross-sectional areas at any location in the pipe, and that's measured in meters squared. And V1, V2, those are the speeds of the fluid at points 1 and 2, and that's measured in meters per second. So the continuity equation can help us find the speeds of a fluid at various points in the pipe, but A times V is also equal to the flow rate. So if we know the flow rate, we can find the speed as long as we know the cross-sectional area of the pipe. So this is going to lead us to Bernoulli's equation. So Daniel Bernoulli was a Swiss physicist, and he derived an expression that relates fluids to its pressure, speed, and elevation. Now this was not a new concept, but conservation of energy being applied to an ideal fluid. And all other considerations being equal, when a fluid moves faster, the pressure drops. So let's look at this same pipe where we have those cross-sectional volumes 1 and 2, where their volumes are still equal. And we're going to mark the distances D1 and D2 for each of those sections of the pipe, and cross-sectional area A1 and A2 as well. What we know is that the fluid is going to be moving from left to right. This is important because if it's moving from left to right, what that tells us is that the pressure pushing on the left side is going to be greater than the pressure pushing back on the right side, which is why the fluid flows through the pipe from left to right. Now we also need to know the height of the pipe from the lowest point, so we'll call that Y1 on to the middle of the pipe on the volume 1, and we'll call the height from the lowest point of the pipe to the middle of the volume 2, Y2. So we have a bunch of different things marked up on this diagram, but what we're going to use is the work energy theorem to help us find this equation that Daniel Bernoulli derived. So we know that net external work is equal to the change in the mechanical energy of the system. Remember, mechanical energy is just potential plus kinetic energy. And we know that work is equal to force times distance. So we can substitute work as F1 D1, so the force that's being applied on the water on the left side, minus the force that's being applied on the right side across that same distance. And then we can substitute the change as the second amount of mechanical energy, potential and kinetic, minus the first through that first volume. Now we also know from previously that force is equal to pressure times area. So we can substitute that in for F1 and F2, so we get P1 A1 D1 minus P2 A2 D2. Now, the next thing we're going to do is we're just going to substitute in the equations for our mechanical energies. So we know that potential energy, that's gravitational potential energy, so that's mgy, and we'll use y2 and y1, and kinetic energy is 1/2 mv squared for each of those points through the pipe. So we're looking at the volumes of the speed through the volume 1 and volume 2. So looking at that equation, we're going to take and collect all of our one terms on one side, so the terms that go through the first volume and the ones that go through the second volume. So that's going to give us this equation of P1 V1 plus mg delta Y1 plus 1/2 mv1 squared equals P2 B2, etc. Now, what we're going to do next is we're going to divide each of our terms by the volume because we know the volume of 1 and 2 are the same. So if we divide each of those terms by volume, we're going to simplify this equation a little bit. It's still going to be long, but we're going to simplify it a little bit. So we know the volumes are the same at 1 and 2, so we're going to cancel that out and leaves us with P1. We can cancel out V2 in the volume, and that's going to leave us with P2. Now, the next thing we're going to do is we know that density is equal to mass divided by volume. Now, we're not really going to know the mass that's passing through, but we will know the density. So we can see that in each of those terms, we have an m divided by v. And we can change m divided by v to density, so that becomes rho g y1. But we also have it here, 1/2 rho v1 squared. Then we can change that to rho g y2 plus 1/2 rho v2 squared. And this gives us Bernoulli's equation. So that tells us that the pressure, gravitational energy, and kinetic energy at any point in the pipe is equal to the same values in a second point along that pipe as long as the fluid is flowing through. So if we look at that, that tells us that the pressure, gravitational energy, and kinetic energy are going to be constant at any point throughout the pipe. So that's why Bernoulli's equation works. And we know that pressure, P is pressure, and that's measured in pascals. And we know that density in a fluid is kilograms meters cubed. G is a gravitational acceleration constant. Y is the height from the lowest point, and then V is the speed of the fluid at any point in the pipe measured in meters per second. So let's look at some tips and tricks to use for Bernoulli's equation. So first, let's look at P1 and P2. Now, oftentimes, these are going to be the same as the water's flowing through the pipe, and these values will be given if they're different, or the equation will ask for pressure to be solved. Now, if the pipe is open to the atmosphere on one side or both, then that's just the P naught, which is 1 times 10 to the 5th pascals, unless it's stated otherwise. And that value is on your front cover of your formula sheet. So let's look at Y1 and Y2. Now, if the height, those are the heights from the lowest point to the middle of the pipe. So what you define as the lowest point, like we did with conservation of energy. Now, if there is no change in height, y1 to y2, then that means the rho gy's terms cancel out because there's no change in height. Those values are going to be the same. We could put in a height and calculate it, but they would cancel out. Now, using the continuity equation is how we're going to find one of the speeds. So we'd probably be given one of the speeds, or we can solve for those speeds in terms of the other. So we can use the continuity equation to write an expression for V2 in terms of V1. So if we wanted to solve for V2, we just divide by A2, and that would give us an expression for V2. The height change does not affect the speed. Only a change in the cross-sectional area affects the speed of the fluid. Let me say that again. Only the cross-sectional area changes the speed. The reason for that is because the water behind it is still moving at that same flow rate. It has the same flow rate. So therefore, there's work being done behind the water that's passing through the section of pipes that we marked. So there's work being done. So the kinetic energy is not going to change, but even though the gravitational energy is changing. So it's not like a ball being thrown up in the air that slows down as it gains gravitational potential energy. So the only thing that affects the speed of the water through the pipe is the cross-sectional area. So this is an introduction to fluid dynamics. I hope this was helpful, and I hope you have a great day and an even better tomorrow. If you found this video helpful, click the like button down below and subscribe to my channel, Cabby Coaches, and follow me on Instagram and X at Cabby Coaches.